Okay, let's get started. Everybody have a fantastic weekend. Glorious weekend. Excellent. All right, well, let's begin with some announcements, changing things up. You have homework due tonight, and you have a test on Friday. I've posted a review to Canvas along with the solutions to that review. I'll be going over those solutions on Thursday, a little more in depth. Okay. So you make sure to look at that before you take the exam. That'd probably be helpful. The exam should be very similar to the review I posted. Okay. So are there any questions about anything going on here? Anything like this? Okay, then let us get started. So last time we talked about concavity and the second derivative tests. Okay, so let's review what we learned. Find the open intervals on which the following function is concave up or concave down. So concavity is entirely related to what? Is it just the function itself? Is it the first derivative of the function? Is it the second derivative of the function? The third derivative of the function? What is concavity related to? Second derivative, exactly. So in order to take the second derivative of this function, I should probably take the first derivative of this function. So what is f prime of x for us? Well, what's the derivative of e to the x?
E to the x.
E to the x. Perfecto. And then minus the derivative of e to the minus x. What is that? How do I take the derivative of e to the minus x?
Isn't that just plus EX?
So we're gonna have this is a chain rule problem, right? E to the minus x. I know I take the derivative of e to the plus x, but I need to take the derivative of e to the minus x. So I have an outside function and an inside function. Let's do the easy one. What's the inside function here? Negative x, perfect. And what's the outside function? E to the x, shoo, wow. Take a derivative. So what's the derivative of e to the x with respect to x? Just e to the x. Yeah, we just did that one. And then what's the derivative of negative x with respect to x?
-1.
-1, perfect. So then the derivative of e to the minus x, well, I'm subtracting it, so I subtract there. This is just from that minus. And then times e to the, I plug this in here, e to the negative x times a -1. Very good. So this is equal to e to the x plus e to the minus x. So that's the first derivative. Now I take a derivative of that. What's the derivative of e to the x? E to the x, yeah, it hasn't changed in the last 10 seconds. plus, what's the derivative of e to the minus x? Perfect, e to the minus x times -1, we just did that right there. So plus minus e to the minus x, which is e to the x minus e to the minus x. Okay, so this function, fun fact, when you take two derivatives, you get the function back, you get the function itself. That's pretty neat. So I want to see where this is. Well, I want to see where the original function is concave up and concave down. So how is that related to the second derivative? The original function is concave up, where what?
Where f double prime of x is negative.
That's where f is concave down. So f is concave down wherever f double prime, I'll put x's here, is negative. Yes, and f is concave up where f double prime is positive. But it's all got to do with the sign of f double prime. Okay, so f double prime of x, I want to find out, let's find where f is concave down first. So I want to find where is f double prime of x less than 0 for concave down. Well, that means I need to solve where is e to the x minus e to the minus x. Where is that less than 0? Okay. So I'll add e to the minus x to both sides of this inequality. I get e to the x is less than e to the minus x. And then how do I solve this inequality here? What should I do to both sides? I want to solve e to the x is less than e to the minus x.
Would you use the natural log?
Yeah, take a natural log of both sides. Very good. When I take the natural log of the left, that's just going to give me e, natural log of e to the x. Well, that's just x. Those undo each other. This is going to be less than or equal to natural log of e to the minus x. So that's less than negative x, right? So then from there, I can add x to both sides. Plus x. Plus x. I get 2x is less than 0. So what does that tell me about x? If 2 times x is less than 0, then what?
X is less than 0.
Less than 0. Very good. So that means f is concave down on the interval minus infinity to 0. Okay. To solve the other inequality, to solve where is f double prime of x greater than 0, well, we can just flip the sign of this, right? We're going to get e to the x minus e to the minus x is greater than 0. And you go through the go through all the same steps, and you get that f is concave up on the interval 0 to infinity. Now, before I made a big table with all of your values, and we looked at the sign at test points and stuff. Still do that. I'm just trying to go through this example quickly so that we can get to other stuff. So are there any questions on this example other than where is that table? I just answered that. No, where f double prime of x is equal to 0 is not called a critical number At least it's not called a critical number for f. That's technically a critical number for f prime, but I'm never going to say that. Yeah.
So, actually, never mind.
Okay. Good question. Good question. Any other questions? No, you can still do a table for f double prime. The question was, so we don't do a table for f double prime? I didn't, but you can still do that. I'm just trying to get through this quickly. Okay. Any other questions? Okay, so now we're going to talk about limits at infinity. Okay, so limits at infinity. So we have almost everything that we need to be able to draw a really accurate sketch of a graph with just a handful of information. And that handful of information is stuff like the x and y intercepts of a function and the vertical asymptotes and the critical numbers, concavity, increasing and decreasing. All of that information, when you put it together in a table, which is not that tough to do, you can get a pretty accurate sketch of a graph. The only thing we're missing is what's called the end behavior of a graph. Okay, and so this end behavior, what I mean by that is what happens when x goes off to plus or minus infinity. Okay, this should really have a plus or minus here. Okay. So as x gets really, really big, what's happening to f of x? Is it also getting really, really big? Or maybe it settles down. Maybe it is sitting at some value when x is really, really big. Okay. We don't really know how to handle that yet, but we actually do. We just haven't really talked about it. Okay. So as an example, using a calculator to describe what happens to the following function as x approaches positive infinity. Okay, so f of x is equal to 3x squared divided by x squared plus 1. Okay, so when x is equal to 0, what do we get for f of x here? Well, I'm going to get 3 times 0 squared over 0 squared plus 1. So that's 0 over 1. And scientists say that that is 0, right? Okay, what happens when I plug in 1? What do I get? 3 halves, excellent. When I plug in 10, what am I going to get? Well, on the top, I'm going to get 3 times 100. In the bottom, I'm going to get 100 plus 1. So I'm going to get 300 over 101, which is very close to 3, right? So a little bit less than 3. Yeah, and then the next line, 100 squared. In the top, I'm going to have 3 times 100 squared. Well, that's going to be 3 with 4 zeros. 1, 2, 3, 4. And then at the bottom, I'm going to have 1, 1, 2, 3, 1. That's even closer to 3, right? That's even closer to 3 than at x equals 10. And then in this box here, for 1,000, I'm going to have 3 with 1, 2, 3, 4, 5, 6 zeros. And I'm going to divide by 1, 1, 2, 3, 4, 5, 6. There we go. Divide by, what, 1,000,000,001? 1, 2, 3, yeah, 1,000,000,001. Okay. So what number does it look like we're approaching here? Yeah, even though the top is clearly getting very, very big, the bottom's getting very, very big at the same rate, right? And when I do that division, I'm always going to have something a little bit less than 3. But as I get bigger and bigger, as x gets bigger and bigger, it's getting closer and closer to 3. Okay, so the idea of a limit at infinity is still just the exact same idea of as what we had before with a limit. But now instead of x approaching one value, you're just letting x get very, 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 very big. Okay. So I am going to show you the technical definition of a limit at infinity. I'm going to use it to prove one result, and then from that one result, we're going to use that for all of our other results. Okay? Are there any questions on this example? Pretty self-explanatory, I think. So in order to handle this systematically, so that we don't have to keep making these tables as x gets very big, we're going to have to define what we mean by limit at infinity. Okay, so by limit at infinity, I mean the following. Let L be any old real number. The statement that the limit as x approaches infinity of f of x is equal to L means that for every epsilon, remember this is epsilon, for every epsilon greater than 0, there is some number m so that f of x minus L in absolute value is less than epsilon whenever x is greater than m. Okay, and all this means is if I have some function, here's L, then the limit as x approaches infinity of f of x is equal to L means that once x is bigger than m, it has to stay within this band here of size epsilon, that's epsilon, around L, once x is bigger than m, okay? That's all that means. Okay, and for the limit as x approaches negative infinity, it's almost exactly the same, only instead of some m bigger than 0, we need some n less than 0, so that whenever f of x minus L, or sorry, whenever x is less than n, that guarantees that f of x minus L is less than epsilon in absolute value. Okay, so the second one, just take the graph that we drew and flip it. It goes off to negative infinity. Okay. So like I said, I'm only going to use this once. And then well, everything else we're going to bootstrap off of one result that I'm going to prove. Okay. So I don't really care if you know this technical definition. So once we do have that technical definition, though, it lets us define a horizontal asymptote of a function. And that horizontal asymptote is just if f of x does have a limit as x approaches infinity, which it doesn't have to. Obviously, if you just think of f of x is equal to x, that doesn't have, it never settles down, right? It just gets bigger and bigger as x gets bigger and bigger. So functions do not have to have limits at infinity. Okay, so the line y equals L is a horizontal asymptote of a function if either the limit as x approaches infinity of f of x is equal to L, or the limit as x approaches minus infinity of f of x is equal to L. Okay, so all that means is that if I draw a function, that was awful. If I draw a function here, straight line, straight line. Here's a function that has a horizontal asymptote, okay? Some people, you might have learned before, you might have heard this word horizontal asymptote or these words horizontal asymptotes before, and someone might have told you that the function can never cross the horizontal asymptote. That's not true at all. The function can cross the horizontal asymptote as many times as it wants. It is totally possible, and it happens all the time, that a function crosses its horizontal asymptote. It can cross here. It could also do something like this. It could be like shoo, and then it can oscillate around the horizontal asymptote. That's also fine. The idea is it just needs to sort of settle down on that one value as x gets bigger and bigger and bigger and bigger, but it can totally cross the horizontal asymptote. Okay. So that's the last piece of information that we really need to be able to sketch graphs accurately, okay, that we didn't really have or use before. So the main theorem we're going to be using to calculate limits at infinity is the following. Okay, so if r is a positive number, so r is bigger than 0, then the limit as x approaches infinity of 1 over x to the r is equal to 0. Okay, and then if 1 over x to the r is defined for x less than 0, then we're going to have the limit as x approaches negative infinity of 1 over x to the r is equal to 0. Okay. These make intuitive sense, but let's prove them using that technical definition. So with any of these technical limit definitions, I need to start off by saying let epsilon be greater than 0. Okay? You have to write a really fancy L when you do that to make it accurate. All right, so someone walks in, gives me an epsilon and says, I want you to make the function within epsilon of this limit here, 0. Find this number m so that when x is bigger than m, the function is within epsilon of the limit. Okay, so I want to show, or really want to find m greater than 0 so that if x is bigger than m, then 1 over x to the r, 1 over x to the r, and really in absolute values, really I would do 1 over x to the r minus 0 is less than epsilon, right? Okay, so just like with the other technical limit proofs, we're going to start here and work backwards to find out what m has to be. Okay, so let's do that. So I'm going to say 1 over x to the r minus 0 in absolute value. First of all, we're looking at a limit as x gets really big, or x goes towards positive infinity. Okay, so this is equal to, when I subtract 0, nothing happens. And I'm taking the absolute values, but what sign does 1 over x to the r have? It's positive. We're looking at the limit as x goes to positive infinity. So 1 over x to the r is already positive. I don't need the absolute values to muddy things up. Okay. I want to show that this is less than epsilon. Well, okay, this isn't that hard to do though, right? This is, we can just flip both sides, but when I do that, x to the r, 1 over epsilon. When I do that, what do I have to do with the inequality? I also have to flip the inequality, right? Another way you could think about it is you could multiply, you could sort of cross multiply, right? I don't like to use those words because people use them wrong all the time. So instead, we're just going to flip everything. We're going to flip both sides and flip that inequality. Okay, and then what do I need to do? It's not natural log, in case anyone was thinking natural log. If this was x squared, if this was x squared is greater than 1 over epsilon, what would you do next? I'd take the square root, right? If this was x cubed is greater than 1 over epsilon, what would you do? Take the cubed root, right? So whatever r is, I just take the rth root. But that's the same thing as raising both sides to the 1 over r. Okay. So then, x is greater than 1 over epsilon to the 1 over r. This is technically only valid if these are both greater than 0, but we know they are. We assumed that they were. Okay, so that means what should I take m to be? What should I take m to be? I need to find that number m so that when x is bigger than m, I have 1 over x to the r is smaller than epsilon.
M needs to be greater than X.
M needs to be, well, we want x greater than m, actually. We want x greater than m. So I need to find this m. I need to find m so that x bigger than m implies 1 over x to the r is less than epsilon. So why did I do all this work over here? And that work over there, I started on this side and got to here, right? I got to x is bigger than something. So what should m be? M is that thing that x needs to be bigger than. Perfect. Perfect. M is this 1 over epsilon to the 1 over r. Okay. So this is why we did all this work. This is why we started here and got down to here. Because every step was reversible, right? Now that I have this, I can say, okay, well, we'll start here, and then we can backtrack to get back to where we wanted. Okay, that's the whole point of these epsilon proofs, is you work backwards from what you want, you get what you need, and then once you get what you need, you get back to what you want. Very circular, but it works. Okay. Sounds like a Stones song or something. Questions on that? We're done. Does everyone see we're done? We found the number m that guarantees this. And in the case that x is less than 0 and 1 over x to the r is defined, the proof is exactly the same. Except there's a few negatives floating around. Okay. But the key takeaway here is the limit as x approaches plus or minus infinity of 1 over x to the r, as long as this is defined, is equal to 0. If r is bigger than 0. Okay, well, let's use this to find some limits. So, example 1, find the following limit. The limit as x approaches infinity of 5 minus 7x to the third. Well, how do I do this limit? equal to the limit as x approaches infinity of what? You can't really just plug in quote unquote infinity anymore. That's infinity is not really a number, and if you try plugging in infinity, that's going to give us some weird results sometimes. So let's use that result I just proved, though, in combination with the fact that remember that the limit of a sum is the sum of the limits. So this is the limit as x approaches infinity of 5 minus the limit as x approaches infinity of 7 over x cubed. And really the 7 we can pull out in front here, right? So what's the limit as x approaches infinity of just the constant 5? Is that changing with x at all? Does 5 change with x? No. So does the limit as x approaches infinity, will the limit do anything? No, this is still just 5, right? This isn't a derivative. This is just a limit. And so no matter what x is, the function we're just looking at there is 5. So as x approaches infinity, well, again, it doesn't matter what x is. I'm still getting 5 there. Minus 7 times the limit as x approaches infinity of 1 over x cubed. But what is that limit? Is this related to that limit I just proved? Yeah, with r equal to 3, right? So what is this? What is that limit? This is 0. Very good. 0. And so we're just left with 5 here. Questions on that? Find the following limit. The limit as x approaches infinity of 9x minus 5 over 3x plus 7. And this reminds me, if anyone's taken this class before and knows a shortcut to find this limit, and you do that on the next exam, when I don't say you can use that shortcut, then you're not going to get any points. Okay? So, just so everyone knows, if you haven't taken this class before, then don't listen to anything I just said. Okay, so this example, if we just look at the limit as x approaches infinity of the top and the bottom, oops. Well, then if I just try to like plug in infinity, which again, you shouldn't really do, then I'm going to get something. If I plug in a very, very large number into the top, I'm going to get 9 times a very, very, very large number minus 5. That's still a very large number. But in the bottom also, I'm going to get 3 times a very, very large number plus 7, which is still a very, very big number. So I can't just plug in. You should never just plug in infinity. And it doesn't look like I can use that result that we just showed But for these types of functions, there's a trick we can do. I'm going to multiply the top and bottom by 1 over x. So in doing that, I haven't changed the value of the function at all, because I'm just multiplying by 1. But then when I do that, this is the limit as x approaches infinity. When I distribute this, well, 9x divided by x is going to leave me with 9 minus 5 times 1 over x. Well, that's just 5 over x divided by the limit as x approaches infinity of, again, distribute here and here. 3x times 1 over x, that's just 3, plus 7 times 1 over x, that's 7 over x. So then, what's the top limit? The limit as x approaches infinity of 9 minus 5 over x. This is very similar to the one we just did, right? Very, very similar. So I'm going to get, well, what's the limit as x approaches infinity of just 9? That's just 9.
9.
Yeah, this is equal to 9. And then what's the limit as x approaches infinity of minus 5 over x? That's 0. Very good. So 9 minus 0 divided by, what's the limit as x approaches infinity of just 3? 3. Very good. Plus, what's the limit as x approaches infinity of 7 over x? 0. Very good. So I'm going to be left with 9 over 3, which is 3. So you might have learned in high school, maybe if you had learned about horizontal asymptotes before, if they told you a certain trick that I'm going to prove here in a second, you might have known that already. If you did, that's great. If not, you're going to learn a trick here in a minute or two about how to calculate this quickly. Okay. Find the following limit. The limit as x approaches negative infinity of 3x squared minus x over 4x minus 1. Okay. So we're going to do the same trick we did last time. I'm going to divide top and bottom by 1 over x. Okay. So this is the limit as x approaches infinity, negative infinity, sorry. Well, 3x divided by x, or sorry, 3x squared divided by x is 3x, minus x divided by x, well, that's just a minus 1, divided by the limit as x approaches negative infinity of 4x divided by x is 4, minus 1 divided by x is just 1 over x. Okay, so let's look at the bottom. The limit as x approaches negative infinity of 4 minus 1 over x. Well, what's the limit as x approaches negative infinity of just the number 4? Wait, what did you say? Yes, 4. I thought you said 1. Sorry. Yes, it's 4. Very good. 4, and then what's the limit as x approaches infinity of, sorry, x approaches negative infinity of 1 over x?
0.
0. So I'm going to get 4 minus 0 down there. Up top, what am I going to get? The limit as x approaches negative infinity of 3x minus 1. Well, let's just look at a graph of 3x minus 1 really quick. Good enough. 3x minus 1 goes through 0 minus 1, 1, 2, 3 over 1. And so 3x minus 1 is doing that. Does it look like that's going to settle down to any one number as x goes to negative infinity, goes all the way to the left? No, right? The top is going off to negative infinity. Uh-oh. Why are you doing this? There we go. The top is going off 3x minus 1. As x gets very, very big in the negative direction, this is just going off to negative infinity. Okay, and so we could say that this limit is negative infinity, or you could say that the limit does not exist. I would prefer the limit here that you put negative infinity. Okay. Questions on that? So we did sort of 3 distinct cases here, right? We did, and if you've seen this before, you know what I'm building up to. We did the case here where the degree of the bottom is bigger than the degree of the top. We did the case where the degree of the bottom is equal to the degree of the top. And we did the case where the degree of the bottom is smaller than the degree of the top. Okay, those are your 3 cases that when you're looking at limits at infinity of rational functions, those are the 3 cases that you can have. Okay, so if you're looking at the limit as x approaches plus or minus infinity of some rational function, and by rational function, that means we're looking at something like this, where p and q are polynomials. Okay. Then if the degree of the numerator, does everyone know what the degree of a polynomial is? The degree is just the biggest exponent that you see when you look at the powers of the polynomial. Okay, so the degree of a polynomial, biggest exponent. Okay, not necessarily the first exponent. Sometimes you might write 1 minus x squared. That's still a degree 2 polynomial because the biggest exponent you see on the x's, I guess I should say biggest exponent on x. The biggest exponent you see on the x's is 2 in that case. Okay, so if the degree of the numerator is smaller than the degree of the denominator, then the limit of the rational function is 0 as x approaches plus or minus infinity. Okay. If the degree of the numerator is equal to the degree of the denominator, then the limit of the rational function is, well, if we write out p of x and q of x in standard form so that their highest exponent occurs first in the sum, then the limit is going to be, well, let me just write out p of x and q of x up here. Oops, 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 oops. I'm going to write out p of x is equal to a x to the m plus other stuff, and q of x is b x to the n plus other stuff. Okay, so if m and n are equal, those are the both of those are the degrees, then we're going to get a over b. Okay. And then the last line, if the degree of the numerator is bigger than the degree of the denominator, then the limit of the rational function is plus or minus infinity. And you have to determine the sign from the actual function itself. Okay. So let's look at this example here. Find the limit as x approaches negative infinity of x cubed minus 7x squared divided by 14 plus 5x to the third. All right, so which of these three cases does this rational function fall into? First of all, what is the degree of the top? Good. Degree of top is 3. What's the degree of the bottom? It's also 3. Very, very good. Highest exponent is 3 in both the top and the bottom. So the limit as x approaches negative infinity, well, you just divide the coefficient on the x to the third term, okay? It's always you divide the coefficients on that highest order term. So this is just going to be, well, the coefficient here is 1, right? The coefficient on x, just x to the third, that's 1 over 5. And the way we can actually prove that, instead of just trusting that I'm giving you the right information, you can actually prove this by doing exactly what we did before, only instead of dividing by x, you could divide by, you could divide the top and bottom by x cubed. Okay, and when you do that, you'll end up with this 1 minus 7 over x in the top, and then 14 over x cubed plus 5 in the bottom. Okay, and then as x gets very big in the negative direction, this part and this part are both going to 0, right? And so you'll be left with 1/5. So that tells us then that this rational function has a horizontal asymptote, by the way, at y equals 1/5, okay, is a horizontal asymptote. Okay. So that's where we're going to stop today. Tomorrow we're going to pick up with more of these limits at infinity, and then we're going to get a little bit into curve sketching, not a full dive into curve sketching, but we'll get a little bit into that. Thursday's exam prep, Friday's exam. You guys got this, okay? If you have any questions, stick around and ask me. Otherwise, please wipe down your desks as you go. And I have office hours today. Remember that, 1 to 3.
Thank you.
Thank you.
Thank you.
Thank you.
Thanks.